Dear students, my name is Dr. Vivek. Today we are going to discuss about, or we can say we are going to learn about Schrodinger equation. So Schrodinger equation is basically a mathematical tool or a mathematical equation to describe to describe the behavior of a microscopic particle. So here questions arise: what is the difference between macroscopic particle and microscopic particle? Suppose light fall on a particle and it affect the particle, it means that is a microscopic particle, or it doesn't affect the particle, that is called a macroscopic body or a particle. So Schrodinger equation deals in the realm of quantum mechanics, and quantum mechanics deals with the microscopic subatomic particles behavior. So let's start with our discussion about Schrodinger equation. There, first slide you can see. Before we are going to Schrodinger equation, we have to know something very fundamental things. One is what is photon momentum. As we know, the light is behave like a wave, and it is also behave like a particle. So what is particle and what is light? What is wave? You can understand this with the very basic definition, like the localization of space is called particle and delocalization of space is called wave. So as we know, light possesses a dual nature, wave nature as well as particle nature. So when we are deal with the particle nature, we knew that the light can be propagated by their quanta, and we know these quanta as a termed as a photon. This packet of light can travel in a packet of bundle, carry energy h cut omega equal to h cut omega, that is called a photon. That is that behavior described by the physics described by the Max Planck. As we know, when light travel in a free space, the photon momentum is nothing but it is you can see from the slide 1 equal to Cp, where C is the velocity of light and the P is the momentum carried by the photon light. So P is nothing but that is simple E by C, or E, as we know that the energy carried by the each quanta of light, that is photon, is h cut omega, where h cut is the reduced Planck constant that is given by h upon 2 pi, and omega is the angular frequency of that photon, and c is the velocity of light. And we know that omega by c is nothing but it is a k wave vector. So E is nothing but that is equal to h cut k. And when we are deal within an optical material or in any material, when light propagate, then just this relation simply replace the velocity of light in a medium by the velocity of light in a medium, like Vp. Here Vp means the phase velocity. And after this, before we are going to the another section of Schrodinger equation to describe how we get the Schrodinger equation, first we have to understand the very basic phenomena, that is Heisenberg uncertainty principle. Heisenberg realized that the subatomic particle, the position and the momentum of that microscopic particle, we can't measure them simultaneously. What do you mean by we can't measure them simultaneously? Means that the position, the uncertainty in the position is described by delta x, and the momentum is described by delta p, and Heisenberg approached this result, delta x delta p must be greater than equal to h upon 4 pi equal to h cut upon 2, where delta is the uncertainty in position and delta p is the uncertainty in momentum. As you can see, what this relation signifies, that when we are more accurately, when we want to measure the position precisely, means delta x should be minimum, you can minimize that, and so you have to pay in the another variable, that is p, momentum. So delta x delta p is basically a conjugate pair, or there is some type of there is a relation between these two, is relation that is called a conjugation of relation. They are conjugate pair, means p is nothing but described by I h cut del by del x. There is a inverse relation. So Heisenberg uncertainty principle is a very fundamental principle and very basic principle in quantum mechanics, and as you see in my further slides, the uncertainty is basically an inherent property of a wave function, and you can't underestimate or you can't neglect the uncertainty as total. There is always uncertainty in the measurement. So from the best application of this uncertainty principle, suppose you know, all of you know the hydrogen atom. What is the hydrogen atom? Hydrogen atom, as you know, atom is built up of nucleus and an electron. So central part is a one proton and one electron is revolve around a first orbit of this nucleus, or this atom, sorry. So this is the hydrogen atom, and as we know, the mass of a proton is 2000 times heavier than the electron. So and these are the two, you can treat them like a two charge particle. Proton has a plus charge and electron has a negative charge, and we know that the very fundamental force to describe the force between two charge particles, or a potential between these two charge particles, are described by a Coulomb force. So the Coulombian force or a potential energy to describe between this attraction electron as well as proton, or Vr, is equal to minus E square upon 4 pi epsilon naught r, where potential is only depends on a radial distance or a radial part, not it's free from the, or is independent from the azimuthal part or a angular part. For the ease of the mathematics here, E is the charge of each particle and epsilon naught is the permittivity in free space. As we know the kinetic energy, as we will know, as we are knowing the kinetic energy from our 10th or 11th class, kinetic energy is just a half mv square, that is p square upon 2m, where p is mv, that is the momentum, mass into velocity. So what is the total energy? Total energy is just the kinetic energy and plus the potential energy. So we will get this equation, p square by 2m minus potential energy. Here in this slide we have plotting a graph of energy versus radius. Here A is the Bohr radius, it is a distance of electron from the nucleus or a proton. So how we can calculate this? So there is a simple procedure. So at the Bohr radius, the energy should be minimum state. So minimum state in a hydrogen atom is basically its binding energy, that is minus 13.6. And as we know, if we want to calculate the minimum or maximum or a extremum of any function, we have to just deal with a differentiation of that function with respect to some variable, and makes that them equation equal to 0, we will get our result. So we apply here at energy, we take a differentiation with respect to the variable r, where r is the A is the Bohr radius, basically that is the distance between the electron from the center of the nucleus of center of the atom, hydrogen atom. So it's a simple mathematics, d by dA, we will take it's equal to 0, and we find that the value of Bohr radius is nothing but 0.5 angstrom. So 5 into 10 to the power minus 10 meter is the distance of first electron from the nucleus, from the center. Another one property of important property of a quantum mechanics is the de Broglie wavelength. As we know that the microscopic particle possesses a dual nature. So or we know that light has a dual nature, it acts a wave as well as a particle. Can particle also can behave like a wave? Yes, it's true. So de Broglie said that basically established a relation between the wavelength describe any wave. So wavelength is inversely proportional to the momentum by a constant that is called Planck constant, lambda equal to h upon p, lambda equal to h upon mv. So where lambda is the de Broglie wavelength of that microscopic particle. As you can see from the formula, if you increase the momentum of a particle, you can reduce the wavelength as much as you can increase the momentum. That's why the condensed matter physicist to probe a microscopic particle, they have a instrument like SEM, scanning electron microscope. There in that instrument basically we increase the energy of a kinetic energy of a or a momentum of a electron and reduce the lambda, and as we reduce the lambda as much as, so we can probe the microscopic or subatomic particle. So this is very good relation. And the wavelength of a particle depends on its momentum just like a photon, and the main difference that the photon has doesn't have a mass, or matter particle has a mass, some mass. And after some time, Division and German did some experiment. They also shown experimentally that the electron is not only a particle, it also behaves like a wave, and this experiment is called a Division and German experiment, very famous experiment, describe a electron diffraction. So if electron poses a wave nature, also poses a wave nature, then electron, you can treat any material as a ion. You can put them here circle describe a positive ion, and electron move this ion. Suppose a electron is coming in this material, so if it is like a wave, it scatter from each atom, and you can just like a your optics subject, you can see, you can make a path difference of these two waves, describing these two waves, and you can you can easily calculate the d sin theta, the path difference, and if d sin theta is the integer multiple of lambda, you will get the constructive interference pattern. So it's also describe the wave nature of a particle, or it suppose the theory of a de Broglie, which said that that the particle possesses a dual nature as like a light. So and this slide simply shows the give you a simple glimpse of the analysis done by the Division German experiment. Here is theory, and the below is the experimental values. So in theory, if you take a E equal to 54 electron volt, you easily calculate the wavelength from that formula h upon p, and you know that E equal to p square upon 2m, then p is nothing but that is the square root of 2me, and you put the values, you will get the you will get the lambda as 0.167 nanometer. And from experiment, Division and German did their experiment, and from that experiment they put the values of d sin theta equal to n lambda, and taking n as 1, that means first order, they were get the wavelength as 0.165 nanometer. You can see that it support the theory, experiment support the theory, and theory support the experiment. So now we are in a stage, so we can describe a Schrodinger equation. So as we know, any microscopic particle behave like a wave, and a very simple wave is from high school physics we know that very simple wave is to describing any wave, very simple mathematics is the plane wave. So plane wave is nothing, that is some psi is some type of wave function or a wave or a variable. Up to this you can consider it as a variable up to this as e to the power I omega t minus kx, where omega is the angular frequency, t is the time, k is the wave vector, and x is the direction in which the wave is propagating. So it is a plane wave, basically it is a plane wave. Psi equal to e to the power I omega t minus kx. Why it is called a plane wave? Because you can see the exponential term that is basically describe a phase of a wave, and you can see the wave vector multiplied by x. So it is here we are only describing a one dimensional motion, or suppose in a arbitrary dimension or in a 3 dimension, you can write it as a e to the power I omega t minus k vector k dot vector r. If you multiply by vector k with vector dot with vector r, you will get kx x ky y plus kz z. So that describes the equation of plane. So the phase is a plane, so it means it is a plane wave equation. You just taking this equation and take a derivative with respect to time and with respect to the space, and as I said, we are dealing with the one dimensional wave function or one dimensional one dimensionality. So we just have to differentiate in a one dimension del by del x. So if we take a time derivative respect and spatial differentiation, we will get j omega e for time derivative and minus j kx e for spatial part. And we know that omega equal to ck is a very peculiar and very known equation. Angular frequency is nothing but the multiplication of velocity of light and a wave vector. So you just square them, and you will and now you taking a second derivative of first derivative, that is del E by del t, you will get a wave equation. So basically del square upon del t square E is equal to c square del square upon del x square E is nothing but that is called a wave equation. So this, what is the Schrodinger wave equation for electron? So as we know, E equal to h cut omega and P is equal to h cut k. As we know the particle energy and momentum, we already know. So Schrodinger guessed that there was some wave like quantity that could be related to the energy and momentum. And as we are considering a simple wave, that is a plane wave, psi equal to e power I omega t minus kxx. Now again, if we take a first time derivative, we will get del psi upon del t e ki power I omega t minus kxx. We take a coefficient of time outside, because we are taking a time derivative. So it's a j omega and exponential term, which we can again write as psi. So j omega psi. So and we know E psi equal to h cut omega. So from that we get E psi equal to h cut omega psi and is equal to minus j h cut, that is a reduced Planck constant, and del psi by del t. And again, if we are taking a differentiation with respect to spatial part, we will get our momentum operator or a momentum px psi is equal to h cut kx psi, that is j h cut del y del x psi. So from these two relation, we can describe a second order differential equation. As we know, for a free particle is equal to total energy is p square by 2m. What do you mean by free particle? Means particle is free to move freely in a space. There is no such type of potential which can affect that particle. It means mathematically V is nothing but that is 0. So potential energy is 0. So free particle described by total energy of free particle described by p square by 2m. You just put there, you will get a equation minus I j h cut del psi by del t is equal to minus h cut square by 2m del square psi upon del x square. That is basically a fundamental Schrodinger equation for a free particle. Again, the last slide, this is our last slide for this lecture or class, the time dependent Schrodinger equation or a time independent Schrodinger equation. So here we write a general form of a Schrodinger equation, I h cut del psi by del t and minus h cut square by 2m del square by del x square psi x comma t and plus potential energy. If we take a v equal to 0, we will get our previous equation for a free particle, because free particle have potential energy is equal to 0. So here I h cut is a physical notation, I is a iota and h cut is a reduced Planck constant, and the left hand side is the total energy term, and right hand side also contain a two term, that is kinetic energy and a potential energy term. So why we multiply h cut I h cut in the left hand side? Because we have to make its dimensionality equally from left and right as well. So right hand side is a kinetic energy. If there is a 1 upon t, there is a unit of time in 1 upon t time second. So we have to cancel that second and put there joule. So we have a fundamental quantity of joule second, that is h cut. So here we have to multiply left hand side by h cut. And why there is a iota? So iota is there because when you are studying or you will read something about time symmetry, so at that time you can think, you can understand that we have to make this time inverse respecting, means not violating the time symmetry. So we have to put iota there. Thank you.